Hello everyone. We're going to start actually. So welcome. My name is André Staltz. I'm a front-end developer at Codestar. And yeah, Codestar is a company, very small company with very passionate developers who are doing big data solutions, Scala development, and some front-end development. And in the front-end area, we're focusing really on functional interactive programming. And that's why we actually André tonight. For who doesn't know, actually André has been here before, actually at the launch event of Codestar some time ago, and he had a talk about Cycle.js, which he developed. And he's also a core contributor to RxJS, about which you will have tomorrow training here. So actually, to go into the program for tonight, we'll first have a talk about functional programming vs object-oriented programming, although I think I shouldn't say VS, maybe better. Yeah, sort of. Well, we'll see. I don't know either. And during the talks, André will indicate when there is time for questions. Definitely after the first talk, because then we'll also have a small break. And then there will be the second session, and that will contain a lot of live coding. Let's see, there are some announcements, of course. I'm sorry. Yeah, okay, sure. Afterwards, there's going to be drinks, and if you want to use Twitter, we have hashtag Codestar17FRP as a hashtag. That's easy to remember. Codestar, the year, right? And functional interactive program, so it's cool. And if you have any other questions, like how to remember this ridiculously long hashtag, ask the people with the Codestar t-shirts. They will also not know, but they will ask me, and then I will tell you again. So I think, yeah, let's give it up for André, actually.
Can you hear me? Yeah. Okay. Thank you for coming. That's the first thing I want to say, because, you know, I'm going to give 2 talks here, and that's it. So all of you guys are just flattering me by just coming here, so thank you a lot. I hope I don't waste your time, and I hope you're going to learn something nice. So this talk is kind of like, you know, I have a background in object-oriented programming. Like, I first coded a lot in C++, and then I did Java for master's thesis. So, you know, that's like my background. And it's only recently that I started getting into functional programming, and then you kind of get this mind-blown effect, and you're like, wow, I should have learned this before. But I'm going to talk about object-oriented versus functional programming, and actually how it's not that much versus. So the question I want to propose today is object-oriented programming just superficially different than functional, like, and under the hood they're the same, or is it that they are fundamentally different under the hood? They're like completely different things. And my answer to you is, it's complicated. It's complicated. And I'm not going to try to answer this properly, actually. So I'm just going to leave it like that. This is a topic we could write books about, do extensive research, discuss, and I'm not here to give a black and white answer to it. I'm here to give a gray answer. And actually, most of my thoughts that I'm going to share here are old, from 1990s and 1980s. So I'm just here, just kind of exposing this kind of stuff. And it's a nice discussion starter and that kind of thing. Yeah. Okay, so let's jump into it. It's common that people just talk about, oh, object-oriented, see, I have a laser, is so much better than functional. And it's also common the opposite. And we're like, no, functional is the best. And then there are people like, no, you need to embrace everything and use Scala with all the different types of things at the same time. Or you need to do object-oriented and JavaScript mixed with functional and everything mixed together. So what is going on here with these 2 pieces? I'm here to show that it doesn't actually make sense to talk about these 2 fields. What it makes sense is to talk about 5 different topics if you look carefully. So those topics are, do we evaluate or do we execute? Do we use objects or do we use closures? Do we allow mutability or mutation is okay or not? When we use assignment, is it just a syntax sugar, or is it a fundamental thing that's actually going on? And are we using types, or is it just dynamically typed and there's no types involved? So these are the discussions that we can have. I don't think it makes much sense to just summarize this whole thing as functional versus object. So let's go into details in each of these. Let's start with evaluate and execute. So what does that mean? Well, in evaluation on the right side, we're talking about getting an expression, like a mathematical expression, and reducing that expression, squeezing it down to a value, which is the thing on the right there. And with execution, we're talking about a sequence of actions that say, go to that piece in memory and get its value, put it in that other piece of memory, set it there, and then do that kind of stuff. And it may sound that these are kind of the same, but they're actually not. So what really defines functional programming is evaluating expressions, and mostly mathematical looking expressions. And imperative programming is mostly what we describe here as performing a sequence of get and set actions. As an example, in JavaScript, we can do, to calculate, let's say, body mass index, on the right, you can use like a function that returns another function that then returns the formula. And then you see that's an expression, and we provide like an initial argument, and then that expression boils down to a value, and you get a value. That's the idea of evaluation. And then we have on the left side a bunch of actions, right? I have set this memory address weight to 70, set memory address height to 177, set BMI address to weight. Take the BMI value divided by height, take that, it's a sequence of actions. It might sound that they do the same, and that's kind of true, just because on the computer we have assembly and we have machine code, and that is actually, in the end of the day, it is imperative. So the right side evaluation will boil down to something that looks like the left side. But that's just because the way that we have these computers works like that. Okay, it's just computers are assembly sort of looking. So, but it means that these are very different. It's not like evaluate boils down to execute always. What's going on here is that the foundation for imperative programming is a computational model called random access machine. It's actually kind of like a Turing machine, but it's just limited memory with some costs there for random access. There's like a theory behind that, and that's you can describe this kind of machine as being capable of doing a bunch of computation. And then on the right side, there's this other theory called Lambda Calculus, which is basically the idea of substitution. So you have this input argument, and you can substitute it with something else. And they have proved that this model can express all the kind of computations that we need. So it's just another model. Imagine that we would have computers that instead of being machine code driven or assembly driven, they would have like Lambda Calculus somehow. Then one thing wouldn't boil down to the other. So, but that's what we mean with functional, is that we mean a Lambda Calculus calculator, kind of. And imperative is a random access machine calculator or programming language. Okay, let's talk about the other aspect, objects versus closures. I'm not talking about classes, if you noticed, because classes are kind of like types, right? And we're not talking about types yet. So both of these are a way of grouping data with functions, okay? So with, let's say, with objects, in typical object-oriented programming, you have that shell, which is the object, and inside that object you have data, and then you have some methods on the shell, which is the encapsulation idea, and those methods are attached to this object, right? And then in the closure, what we have is one of these functions may refer to some data defined somewhere. It's a bit less explicit than objects, because in an object-oriented programming language, you just make an object. And it's sort of pretty visible there. I have an object here. But with closure, it's a bit more, somewhere. Let's see an example of this in JavaScript. Let's start with the left side. It's a bit easier. I have this object, right? It's pretty explicitly there, a greeter object. And it has a piece of data, a Boolean, is female or not, and it has a method attached to it, greet, and then it checks, if it's female, then say Mrs. or Mr. And then on the right side, we have, notice that I don't have greeter, right? I just have greet, because the idea of greeter is more implicit. And there I have a function that returns another function. If you pass me the argument false, then that becomes like the value of is female. In functional programming, we say that this thing is bound to the value false, I hope. Please, Haskellers, don't bash me. But the point is that once you get the function greet, and you call it, it will check what's the value of is female, and that value is inside some closure somewhere. And it's like a bit more hidden, it's a bit subtle. But what's cool is that in JavaScript, you can convert from the right side to the left, or vice versa. And there are some reasons why you should do that sometimes. Like, for instance, in some VMs like V8 in JavaScript for Chrome, usually closures are a bit faster because they have the so-called like shape of the class. You sort of, the virtual machine knows beforehand what kind of shapes it expects, so it makes a struct to sort of optimize for that, and then things are faster. And what we did with RxJS, the rewrite from version 4 to version 5, is that we took all of these kind of closure-looking stuff and we converted all of them to this. Which is kind of interesting because, RxJS is like a functional library, I guess. Then if you look under the hood, there's like this everywhere, and it's a very object-oriented approach. And also I built another stream library called Extreme, and we use this approach everywhere just because of performance. So does that mean that it doesn't matter that these two are completely equivalent and you just use them whatever? No, there's actually another difference, is that with object-oriented programming, you can change the this object. I'm not sure if you can do that in Java. Can you do that in Java? Does someone know? It's okay to say. Well, I don't know, so if you know, yeah. But here, we have the greeter object that worked on, that object that I made there. But then I'm saying, yeah, I'm just going to get this method, I'm going to drop the object, and I'm going to use this other object here that I feel like using. So you can do that. You can get the method that was attached to that object and use it elsewhere. And that's an advantage. But it's also a disadvantage, because it means that someone can change this stuff, and you're like, what is going on here? And sometimes this is undefined, and you're like, this is not good. So, yeah, I mean, it's great. Let's look at the next thing. Mutation versus immutability. So this is cool because one of the things that you hear from functional programming advocates is that when you ask them, why should I use functional programming? And they're like, oh, immutability. And then you check Wikipedia and it says immutability in object-oriented programming and functional programming. Blah, 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 blah. It's not a property inherently of functional programming because, as we saw, functional programming is just an expression of Lambda Calculus, or in a Greek way. And there you go, you have in Java, for instance, here's a final string, and if you call lowercase on that, this S will stay as the same as it was before. Just going to return a new string. So Java has immutability, and it's an object-oriented programming language. And also Haskell has immutability naturally. If you say 2 lower on the S string 1, then string 1 will stay string like it was defined. And then you also have mutation for Java, but I don't need an example of that because you can look at any example of Java and you will find mutation. Right? It's just very common to find mutation in Java, but I'm going to show you mutation in Haskell because people are like, oh, functional programming, no mutation. There you go. So, if you haven't seen Haskell before, this is not hard, trust me. It's pretty simple. I have a function that takes a number, it could be an integer or a float, and it returns a number, but it also does some side effects. And what it does there is that it, creates a reference in memory, and it assigns that, it sets that to 5, and that's y. And then we write 10 to y, and then we sort of return y times 2, right? So you get out 20. You're always going to get out 20. So, no, sorry. I'm actually not using x here. Oh, forgive me. Forgive me. I was supposed to put x somewhere there, but I just ignored x. Yeah, anyway, imagine that this would always give you 2 times x, but it gives you 20 all the time. Anyway, you can write this function in Haskell.
Mutation. What's mutation?
So when we do like a write IO ref, no? Or mutating y?
You're not mutating it. You're changing the world, hey. But that's because you explicitly told that in the type declaration, the IO.
Yes.
It says you're going to change the world.
Yes, yes. So like you are a Haskeller. Yes. So in Haskell, IOA doesn't actually mean that we're mutating. We're not mutating. It's like we are going to mutate. It's a different thing. It's like a representation of mutation. See? It doesn't actually perform this stuff. We're going to get to this point, actually, of like laziness. But here the idea is that this doesn't actually, it's like, I'm not mutating it. I will mutate it. I mean, it's basically the same thing. But anyway, it allows you to do that stuff. But what's cool is that since this function is basically referentially transparent, it means that it's pure. It's always going to return me the same stuff, right? Even though I'm just writing to memory, but it's always going to return the same stuff. It's always going to, in this case, it's always going to return 20. I mean, an effect that will also return me the number 20. So there's this other thing called stref, where you can replace basically everywhere you had ioref, and you can use stref. And there, now I have a function that goes from a number to a number. So because in this case, this mutation, or will be mutation, is not actually, referentially, it's not impure. Okay, it is, because it's pure, I can use the stref, and then this is kind of the same effect when you do a function in JavaScript and you use a for loop inside it. That function may still be pure because inside you're doing that mutation, but it doesn't matter. See? So Haskell allows us to do this kind of stuff, and they're pretty useful actually when you're converting imperative programming with mutation. You can just write it in Haskell, and it's easy. It works. Okay, so I hope you're not tired of it. Okay. We're going to talk about assignment syntax and assignment semantics. So in the previous example, actually, I used this stuff here, this arrow to the left, and it really looks like assignment, right? If you're used to like JavaScript or Java, this looks like assignment, and that's true. Now we use this thing called do expression, up there, and we're basically, I'm kind of pretending that I'm reading the file through, and then I'm assigning its contents to text, and then I use that later. But what it actually expresses under the hood, that sort of is equivalent to this other one, which is like, we don't have the text variable anymore, you see, or the name, because we don't have the idea of assignment. So what I mean here is that it looks like assignment, but it's actually just syntax sugar for something else. It's the representation of tasks being concatenated. And one of the designers of Haskell, Paul Hudak, he said some while ago that he doesn't actually like that syntax stuff. He's perfectly comfortable with just concatenating monadic actions. That's an email that he put some time ago. But then on the other hand, in JavaScript, when you use that assignment syntax, you're actually meaning assignment like as semantics, like it will actually assign something to memory. Those are very different things. And here we don't have like syntax sugar, we actually have that going on. It's different. But the cool thing is that if you allow assignment syntax as sugar, then you can write some Haskell code that looks like this. It's a big piece of code, but what matters is that there's an if then else. There's a kind of like a for loop. There's a bunch of assignments going on. Okay? And I mean, like, you can sort of understand this if you've only done imperative programming. But this does not mean assignment at all. It boils down to an expression, as we talked about, mathematical expressions, which can be evaluated with a value. Very different stuff. Yeah. Let's go to the next topic, which is the most interesting in my opinion, and we're going to talk about it a bit more, which is, do we use types or not? You can ask that question when talking about it. And the cool thing is that you have functional programming languages on the left and object-oriented languages on the left, like Clojure and Python. They are both dynamic, but they're different paradigms. And then you have on the right both functional and object-oriented with types, like Haskell and Java. Types are pretty useful because they help us answer an interesting question, like if x arrow 2 times x is pure. Is that pure function? You can actually raise your hand if you feel like. Is it pure? Yes? No? Yeah? Okay, 2? Yeah, if you get the number 5, you always get out the number 10, right? 5, 10, 5, 10, 5, 10. It doesn't do side effect. But here I'm going to trick you. I made an object called lol, and I set the value of to math random. So every time the function tries to read the value of the object, it gets a random number, and every time I call double, I get a different number. So it's like not pure anymore, I guess. So what is the culprit here? Like, with a typed language, you're able to say like, okay, no more fooling around. You need to give me a number, not an object. And if you give me a number, I will give you a number out. That's what types help us. They tell us what are we expected, like as a contract, you know, you're supposed to give this and you're supposed to get that out. Of course you could, yeah, you have a question?
Can you please explain what you mean by with pure?
Pure. Purity, usually, that's a good question. Can I explain what I mean by pure? It means referentially transparent. What does that mean? That means that every time you call, like you could replace the expression with the value of that expression every time you see the expression. That's what referentially transparent means. So, for instance, with, let's say, this function and the argument x equals 5, you're going to get as an output 10. So every time you see the function call with argument 5, you can just like, replace that with 10, and it's going to be always the same. But that's not the case here. You don't actually have any value that you can always replace with this function call. Imagine that you're doing like a compile time step where you look through all of the cases of double lol and you replace that with a value. If you can do that, then it's pure. So in this case, because I passed a really nonsense object, it's not pure. But in languages like TypeScript and Java, you can still, you know, cast it. You can say, you know, object as any, as number. And then you can pass it to this thing, it's not going to be pure anymore. So, but it still helps us, you know, to give a contract here. And what's going on is that we're actually solving this problem of the, you know, the prank law on the level of abstractions, okay? We're not actually solving this problem. Did you notice that the problem is still there? We can still call this with object. We're just solving it on the level of abstraction in the sense that, like, I know that you can call it with an object, but, you know, on the level of ideas, we're supposed to call it with a number, okay? So that's what types are all about. They're about abstractions. The idea of solving the problems on the level of ideas. It's going to become more concrete. I can show you an example. This is having no abstraction. This is concrete. So I show you a Rubik cube and I say solve it. And then you fiddle with it on a concrete way, and then you solve it. And then you say it's done. With abstraction, you would, I would tell you, please solve this, and you would create a representation an abstract concept of the puzzle, you would solve it in your head, and you would just say, okay, I solved it. And then I go, no, you're just fooling around. Make it concrete. And once you say that, you're saying, convert from abstract to concrete, right? So there's kind of like a two-step, or maybe three steps. I give you something concrete, you go up to the abstract, you solve it in the abstract. And then after a while, I ask you, please give me this thing because I actually want it. And you're like, sure. Then, done. See, so it's like going from concrete to abstract and solving it. And I can give a really good example of this with Haskell, is that once you do that, you gain a lot of flexibility. So for instance, in Haskell, you can represent infinite lists. You can say the list integers is like 1, 2, and etc. And that will actually mean 1, 2, 3, 4, 5 until infinity. And that's what it represents. And that's cool because you can't have infinite lists in like JavaScript or infinite arrays, right? You just cannot have infinite arrays in JavaScript. You can do it in different abstractions, but not with an actual array, you know? And you can do that in Haskell, and then you can say, you know, actually, I actually want 5 integers. And then it's like, oh yeah, sure, I'll produce that concrete thing for you, since now you want something less abstract. But what that gains us, what does abstraction give us? A lot of flexibility, because now we can represent impossible stuff, right? We don't need to actually store them. So, like, we can represent infinite lists, but also all kinds of other restrictions that the computer has. Maybe, you know, like, what if you have a problem that costs n to the power of 3 to solve, and you have another problem which costs n to the power of 4. And if you were to solve those problems individually, it would be quite intensive work, right? But let's say that mathematically, you know, once you combine those two problems together, they boil down to like n log n. That means that like you can compose like expensive stuff on the level of ideas, and then only when you actually need the value, you compute it. So that's cool, and that's what Haskell provides us. And the way that it does that is all through types. And types are this way of saying, oh, you know a list? Yeah, I'm not actually talking about an actual list. I'm talking about this idea of a list, right? So in Java, some stuff are abstract. Like interfaces are abstract, but objects are pretty concrete. And one of the disappointing stuff is that classes are kind of concrete and kind of abstract. And that's kind of the problem, especially abstract classes. You know, they're like abstract, but they are concrete, and it's like, yeah, because classes have this idea of pieces of data, but they also have, you know, methods and maybe abstract methods, so it's kind of wishy-washy, and that creates a lot of problems. In Haskell, actually, very few stuff are concrete. You have like basic types like numbers and other stuff that our friend Haskell can tell us later. But even, you know, abstract data types, ADTs in Haskell, which are very basic forms of data structures, they are abstract data types. See, and that's pretty good because then you can get a bunch of flexibility as well. And the type classes are comparable to interfaces. And so interfaces in Java are kind of like type classes. So what does types give us is that we are able to get reusability. So this thing called inheritance, right? You can inherit, you know, I know that this class of solutions works for these problems. And then you have a different type of problem that's kind of similar, and you say, you know what, I just want to reuse that solution for this problem as well. That's what we can gain here on the level of types. In object-oriented programming, you're reusing classes. But that's like kind of the problem, because you have classes have data, concrete data, and they have some abstract stuff. While in Haskell and functional programming languages, you're just reusing functions. You're not reusing like concrete stuff. That's cool. And the big problem in object-oriented programming, that this is something you can brag to your friends, is your reusability of classes. It's a very bad idea that a lot of people have been talking about, because one of the basic stuff is that it breaks encapsulation, which is one of the basic properties of object-oriented programming. And you know, there's plenty of people talking about this. Inheritance is evil. And apparently there it says that James Gosling, the guy who designed Java in the first place, he said, you know, if I would have to remove something in Java, probably the classes. I didn't say that. He said that according to this very official blog. So yeah, and how is that actually in practice a problem? Let's see here the so-called diamond problem. If you have, let's say, a clickable that inherits object, and you have a rectangle which inherits an object, all of these things have the equals functions, and as you see, like they have that implementation of the equals function. It's like a concrete implementation of that. And then once you say, you know, button will extend both. It's like, well, which equals should I get? And that's kind of the problem with this multiple inheritance thing in Java. Someone very famous said that premature optimization is the root of all evil. And this is kind of what I'm talking about. But let me just change that sentence a little bit. It's like premature concretization or concretization is the root of all complexity. Now, I'm not comparing myself with John Canute, but in a sense, I'm just saying that, like, don't trust this as much as you should trust that, because I'm less than Donald Canute. But my point here is that what happens when you have too much concrete stuff is that you get complexity. Now this works in programming, but it also works, let's say, in software engineering. Let's say you have some requirements, and the requirements are pretty abstract. Like, yeah, we need this web page that does this stuff. Abstract ideas, right? Very abstract concepts, and those requirements are kind of complicated to deal with. But like, if you make that concrete too early, then you get into a lot of complexity later on to make that more flexible. But that's in software engineering. In programming, you often have cases, let's say, where you just make some objects and some classes, and then later on you need to reuse that, but then things get very complicated, and you might end up either getting too much inefficiency, or like, let's say, you know, too many layers of call stacks or stuff like that, or, you know, it's very hard to deal with. So the nice thing is that Haskell can do multiple inheritance. And the reason why is that because it doesn't do premature concretization. It just says everything is abstract. We're going to figure it out later. So for instance, here are some basic type classes that the language comes with, like equals and show and numbers. Here are numbers. And there you see branches like real is a subclass of order, but it also is a subclass of num. And the reason why you don't have the problems with the diamond problem is that these classes just define, like, yeah, we should have these functions. But then later you can say, hey, here's an instance of that function. You're saying, like, here's the concrete part of that thing. And it's actually possible that you define multiple concrete things for a class, and then the compiler will tell you that, whoa, you're doing multiple concrete things for the same abstract thing. And then you can't do that. But it's cool that you can work all on the level of these abstract ideas, and then later you can say, oh, you know, in this case, I actually want that to be this. Okay? I'm talking about instances of type classes in Haskell. I don't want to get too abstract here. Abstract. Yeah, so let's go back to something totally not abstract, JavaScript. Very concrete language. It can do multiple inheritance, and look at that, unreliably, because it's JavaScript, right? Come on. So here's an example. Let's say we have this magic function, multi-inherit. I'll show it to you later. You know, I'm saying that, you know, object will be inheriting 01, 02, 03. And then once we try to get object.a, it's going to look, yeah, I'll get that from 01. And then object.b, and I'll get it from that one. And then object.c, didn't find, oh, there it is, right? So you can inherit an object from many objects. You can do that. How do we do this multi-inherit? It's, boom, yeah. It's not that complicated, okay, relax. Protos is a bunch of objects, right? O1, O2, O3, all of the prototypes. And then I use this new feature called ES6 proxy, where basically every time we try to get a property from the object, we're gonna just iterate over all of the prototype objects. We're literally just going like, yeah, once you do dot A, it's gonna, okay, go here, go there, you know? That's what it's doing. And then the rest is just like, what happens if you set, and yeah, blah, blah. But the big point is just this get here and iterating all the stuff. Well, you could do multiple inheritance, but you know, it's unreliable. So, okay, I'd like to have reliable, you know, multiple inheritance. So it's Haskell, strongly typed, with no premature concretization. And then now is the point in the talk where you go like, I knew it. Haskell is better. Do it, yes. And to that I say, not so fast, my friend, not so fast. In like the first version of Haskell, they had this thing called stream.io. So it was not monad.io, okay? They had stream.io. And then in version 1.3, they introduced monad.io. And look at that. This is where they introduced monad. Haskell's I/O monad provides the user with a way to specify the sequential chaining of actions. And that might sound familiar, and they have here, here's how you do sequential I/O actions. And here's a way that you can concatenate an action that may either set or get with another action. It's like way of sequencing actions. You know what I'm doing? Oh gosh. Do you remember the slide? Perform a sequence of actions. Aha, aha, aha. So, you know, that's the thing that Paul Hudak was talking about. Monadic I/O was sort of made to cater for programmers that are more familiar with imperative programming. And they found this pretty cool abstraction, the monad, which is awesome. It's seriously awesome. If you don't understand, spend 2 years studying. It is awesome. I promise you, it is awesome. But it's awesome. And then they discovered this thing that, wow, we can actually represent this imperative stuff through pure awesome stuff. And that's what they're doing here, you know, they're making it more familiar. And there you go, you have the world of Haskell influenced by imperative languages. And then also there's this other side, which is this paper which sort of introduced type classes is better in Haskell. It's talking about, yeah, type classes. Parametric polymorphism. You can spend 2 years studying what that is. But in the paper they mentioned there, you know, type classes appear to be closely related to object-oriented programming. And then they're like, yeah, there's a lot of stuff to talk about here, you know, like we're sharing a lot of ideas between these fields. So, one of the reasons why Haskell is pretty awesome today, you know, is the monad, which was influenced by imperative programming. Nowadays the monad can be used not just for I/O, but a bunch of cool stuff. And type classes, and you know how type classes are pretty awesome, and they're also related to object-oriented programming. So you could say that Haskell is awesome because it took some ideas from object-oriented programming and imperative programming. So what does that lead us to? Come on, is Haskell the better language, or is it object-oriented? Come on, or what if we just mix everything, right? Everything is going to be all mushy-mushy and mixed with each other. I don't know. I don't know about that. I don't think that's a good idea. Like JavaScript is doing that because JavaScript from the beginning, it had closures, right? It had also objects in the beginning. It's like, huh, why? Both. But it was designed in 10 days, so who cares? And it was inspired by Scheme, which is functional programming. But it's not done in a nice way. It's like, what is that? And also Scala, I mean, I don't know, maybe, yeah. But what I do think is that languages should be coherent. Okay? If you use this approach, then use it in a beautifully designed way that is predictable, so that once the programmer looks at this, he's like, yeah, I think this other thing will be like this. And then he looks at it and he's like, oh yeah, it was like I thought it was. Because it's coherent, it makes sense, everything is consistent. And I'm going to give an example of this. It's called a language called Coca. So what Coca does is that under the hood, it is typed. It uses closures, it uses evaluation, and it's immutable. But on the surface, when you look at the language, it has assignment syntax, it has object syntax. And you're like, huh, what is this thing? So let's look at Coca. It's very cute. Don't be afraid. There you go. Look, a function name, print line, hello world. Come on. This is nice, right? And yeah. Let's look at a better example. Okay, I have a function in code that takes a string and takes a shift integer, and there I return the string mapped in code char. It's like a basic Caesar cipher of cryptography, just like changing A with C and B with D, you know, that kind of thing. But then look down there, Caesar here is, we get the string and we just encode it by shifting by 3. But did you see that? S is a string and encode as a function, right? What's that dot doing there? So what Coca does is that it puts S as the first argument there for encode. So you get the object syntax, but under the hood you have only functions and you have closures. So you're not actually doing objects here. You don't have an object. Okay, it's only functions. But it looks familiar. It looks easy, and I can do this. Pretty nice. And there we go. We also have objects or structs. It's pretty similar to objects. So you can say, you know, it has a field, age, name, and stuff. And then you have like a constructor, which you can think of it as like a class in Java, like a constructor, like a new person, right? That's how we usually do it. And then you get out this object, which would be Gaga, right? But under the hood, when you say gaga.age, as it noticed there, it's not actually .age. It is call the function age on Gaga. So you have the object syntax, but you don't have the object semantics. You have only like functions. And actually, under the hood, a struct is an ADT or abstract data type. So this means that this is actually really not an object. It's an abstract object. Okay? And then we can make it concrete, and that's the thing. One of the big things in Coca is that it also is very strict with effects in a way that's even more strict than Haskell, because it has an effect for like I/O, but it also has an effect for, hey, this can throw an exception, or you know, this is like sort of mutable state in the heap, and that kind of stuff. It says like stateful. So when you program Coca, it's going to be very similar to JavaScript and objects and stuff, but under the hood it has a very strong sort of what they call denotational semantics for all of the effects, and everything is like super checked on the type levels. One of the nice things is that, you know, I would talk about Coca anyway, but I discovered that the guy who designed it, Dan Lyon, I hope I said his name correctly, is Danish, and actually he's from Utrecht. So that's cool. And then I took a look at his PhD thesis, and it was like in the University of Utrecht, and it was funded by Ordina in 2003. So that's a nice way to end the talk. Thank you very much for listening, and we have a couple of minutes for questions.
Thank you. Are there any questions? Yes.
Coca very much looks like what you can do with C# with extension methods. Is that right?
Yeah, extension methods are similar to this idea. That's true. I always liked extension methods in other languages, like I think Kotlin has it, but there's this other one called extend for Java, which has that idea as well. Yeah, you could say it's the same idea, but here they just take it to the extreme where we really don't have objects, while I think C# does.
Yeah, that's true. But what happens if you, let's say you have a type and you define a function for it? So, not sure if I'm wording it properly, but let's say in this example you have person, and on person you add the age. Could you kind of extend that further on in your program and then extend it with another year when 90 or something, to return the year when the person is 90? Or does it have to be in that particular place? where you define the what you do here with the type person. Yes.
Yeah, that's a good question. I would guess that because it's an ADT, you can wrap that ADT in many ways you want in another ADT to add other data, I guess.
So like what you have in C# with extension methods is that it has to know the extension method before you can use it, right? Because if the extension method is not being made available to the system, then you're not able to use it. Is it the same here?
Yeah, if I understood correctly, in Coca you can define a module, that has some functions, and then you can import that module, and then once you do that, you can have all the extensions.
Only then you have the extension method. Okay.
Yeah, it's not like globally defined.
Yeah. So not like an object which has methods.
Yeah. Not like
when
that.
you do a new class, you get the methods for free.
Yeah.
Well, you have to import it, of course.
Yeah, in practice, I'm not sure how it goes.
Thank you.
Another question?
Anyone else?
Hey, so this is a little bit tricky. The question is, what do you think that is the advantage of familiarity? You mentioned it a lot, and you say, okay, I have this language that takes a lot of influences for functional programming language, or some ideas of Computability, but express it in a way that is more familiar. What is the real advantage of familiar? Because when you look at the code, sometimes I see, okay, I also come from a background object-oriented and imperative. When I started to learn functional programming, and I see that the code ends up being more expressive. And today I don't think that when you say, okay, I have this syntax that is similar to object-oriented, but it looks unclear for me. That is actually more clear to have a function that receives 2 parameters sometimes. So what's for you and also that code in a language of the ML family maybe would look more compact and eventually more easy to discover what is going on there than in imperative programming. So
okay, so what's the benefit of familiar is that it's familiar. No, but on a serious level, familiar is a lot about how people perceive the world. I've been reading a psychology book, and when people feel that there's something familiar, they enter into a state called cognitive ease, where they are more likely to accept things. And of course, what if if you're using a language like JavaScript and you're struggling a lot, but it's very familiar and you're in your happy mode there? What if I would tell you actually if you took 1 week to study Haskell, you would solve this problem in 3 days? People still don't learn it. It's a matter of dealing with people. It's quite hard. And I think approaches like this, where Dan is one of the people who helped work on Haskell, made a parsec library and a bunch of stuff like that. He's been working a lot with Haskell. And in this approach, they're saying, what if we just not show functional programming code? And maybe this would be shorter in a real functional programming language, but how much shorter? Would it be half a line of code? Does that really help with readability? I think these are subjective questions and subjective answers. It's hard to say. But it's a good discussion point that we will talk about in the break, for instance. Okay. There's another question.
We'll jump on here.
Hi, so I got the idea that you use imperative and object-oriented somewhat interchangeably. Is that correct?
Not necessarily. When I talk about object-oriented, I talk about objects. In imperative, I talk about sequence of actions. Yeah, that's one of the things I wanted to make clear. But on the other hand, it's also become a term for Java-looking languages. But when I said, for instance, that Coca has some object-oriented ideas, it's especially because it allows the dot syntax on objects, Which kind of sounds like it's object related.
Any more questions? Oh, yeah.
I was fascinated. You brought me on the track by your structure market that inheritance is evil.
Yeah.
I once worked on a code base where they had they were describing disk subsystems, so big bus of disks,
Yeah.
and they started with a structure of, it was C code, of 10 properties. And over the years, it grew to 180 properties. Each of the properties could be of different disk. So it's like an animal, and it can have legs and feathers or whatever. But the frog don't have feathers, but you just don't see it.
Yeah.
So inheritance, it may be evil from a theoretical point of view, would have been very practical from a practical program point of view.
Yeah, until you get into those cases of like animal with wings or animal with fishes, with animal.
Then you can have an hierarchy and types with a struct.
Yeah, but usually when you get into like, if you just go with classes from the first point, at some point you get into a problem, especially with this.
Yeah, but my question would actually be more from, this is nice from a theoretical point of view, but what are the practical consequences programmer of FP versus object-oriented programming? For example, why don't you put more FP? Because it's complex code. Haskell is not an easy language, I guess, for most people. And not all programs are very smart.
Yeah. Well, so, like, I think this is a practical problem in terms of, like, I want to get this done, and then you end up, like, making another class, or kind of makes another class, or another class. So, it's kind of complicated. What Haskell does is that it started with, like, functions and evaluation, and then over time it started discovering, like, let's say, why am I doing this with slides, sorry. Yeah, over time it discovered the do notation, which made it a bit easier for some people. Some people like it a lot. So I think Coca is like the culmination of that, where they said, okay, let's sort of let go of the evaluation syntax. Let's embrace the imperative syntax as a sugar. And that would make things more familiar and more easy, right? So when you look at Coca, it's kind of easy because it doesn't have those problems that you mentioned. I do agree with you that Haskell can be quite hard in the sense, you know, very hard to learn, everything. It's very beautiful as well, so yeah, it's kind of, yeah.
I think the hard part about Haskell is that Haskell somehow forces you to think
You
on
can
a
say
more
in the microphone so people can hear.
My personal experience with Haskell is that it forces me to think on a more abstract way about the problem I have.
Yeah.
And if I don't do that, well, I just don't get it right.
Yeah.
So, and that can be hard. I mean, in all languages, you just write something down and maybe it works, and well, if it's buggy, you'll see that later.
Yeah.
But Haskell really forces you, and then, well, the resulting code has somehow it seems that the resulting code is getting on an abstract level.
Yeah.
But Haskell, in its basics, the syntax, so it's really easy.
Mm. Yeah, like I do see those things that you said, and I totally agree. I mean, like Haskell forces you to think. That's a problem for many people. For many people, they don't want to think. And this goes back to, you know, how people like dealing with problems. Most of the times is that when you tell them, you know, solve this, they just want to fiddle with it, which means they want to, like, do something and then see how it works in the browser. Do something, see how it works in the browser. With Haskell, you're most of the time, well, at least from my experience coding a little bit of it, is that you're like coding in Haskell, you know? You're most of the time just thinking and coding in Haskell. And then after a while, you go and see how it works. A lot of people don't like to think. Kind of sadness of humanity.
And on that positive note, let's go to a break. Until 8 o'clock, please. Brings you